All right, friends.
No, they're like.
Let's figure out some homework stuff. No.
What? Parents like beat them at 13. That happened to my friend. Yeah.
It's a revolution.
And all the babies were gone in one of the other.
There you go. That's for the med class. You want to take that? All right. What? It was I last night, yes?
Yeah.
Yay. I odds. H-I-J. All right, questions. Go for it. Holding horses. 19? Whole thing. All right. Number 19. Okay, ready? Height. Thank you very little. Yep, he's here. What did you do?
I already got one today.
Logan or Grant?
Yeah, I mean, don't judge me till
All right. So here we go. First thing we want to look at is I'm just looking at the denominator of both of those. That denominator is an even number, so that means this is going to be a fourth root, which means I can't have negative numbers. So the domain of each of these is going to be 0 to infinity. So let me pause there. Does everyone understand why?
Yeah.
Anybody stuck on that? Please speak up. Okay. So now I want to divide the two.
Why would 5/4 be if, oh, it's because it's an even number.
Yeah, the denominator's even. All right, so if I look at this, how it's set up now, even though it'll reduce a little bit, you have to realize that the domain here is going to change to a round bracket. Why is that?
Because you can't have
Can't have 0 downstairs in the denominator. So that's going to be 3 to the 1/4, x to the 1/4, bring up the 5/4, add the exponents, so that's going to give me -1, so I get 3 over x. So that's my answer with that domain. Cool?
Yep.
Next. Next question. 2-1?
Yeah.
Okay. Okay, can I move off this board? Cool. All right. These are a composition of a function. Number 21. We have f g at x and g f at x. Is this the right one? Am I looking at the right one?
Yep.
Okay. And they're going to tell us that we have f at x is -x to the half. Okay. And g at x is going to be x plus 4. So we want to go ahead and find the domains of these first before we do anything. So that's the 1/2 power. And that's taking the 1/2 of just x. The negative doesn't mean anything. But think about this. I can plug any number here in for x. So think about what this really means. This is the same thing as that. Do you agree? So then that means that the domain has to go from 0 to infinity here. The domain of this one is not restricted. So it's any of the numbers. Are you okay with both of those? Yeah. All right. So composition of a function. This is something that it looks real easy when I do it, and you get home and you're like, hey, what? And that makes it about normal. So I'm going to try and do this a way that I was thinking about last night might be good. Okay, so I'm going to do this one first. Okay? I'll do this one first. So I'm going to take my g at x, this value here, and I'm going to plug it in. So that means I'm going to take x plus 4, which is g at x, right? I'm going to take x plus 4, and I'm going to substitute that in place of the variable I had for f at x. F at x had negative x to the half, right? So the negative and the raised to the half power both stay there, but the x is going to change. So this right here is going to be replaced with x plus 4. Notice the negative and the half are both still there. Okay, so as we progress through this, so fg at x, I'm going to do negative parentheses to the half. That had been an x, but what's going to go there? This had been an x. What's going to go there instead? X plus 4. Okay? So think about what this, so this is that problem right there. So realize this, sometimes it's easier to see it this way. This means the same thing. Okay? So where do we go with this? You gotta be careful on this one. A couple things to check on.
Can take you out.
So let's look at what the domain of this would be right now. The domain of that right now, yeah, buddy. What's the smallest value I could plug in that still would make this true? Don't worry about those yet.
-4.
Good. So I can go from -4 to infinity. Okay? But let's pause for a second. I heard this analogy from one of the other math teachers. Composition of a function is you're plugging a function into a function. Think of it this way. You guys heard the term lactose intolerant?
Yes.
Like
What is
people,
lactose intolerant?
means it's, you can't deal with the sugar of lactose that's in milk. Okay, makes you fart. Okay? Okay, that too. But so if you're gonna make a recipe lactose intolerant, every part of that recipe has to be lactose free, right? Like I can't take a lactose free recipe and dump it into milk saying, yeah, it's lactose free. Because, well, it might be fun to watch a friend, and what you do is you put saran wrap over all the toilets.
That just ruins your house.
Well, you do it when you're at their house then.
With their ceramic.
Sorry. Okay, now we've also heard of people who have a gluten intolerance, right?
Yeah.
So let's say a person was lactose and gluten intolerant. They couldn't have either.
Just tofu.
Yeah, I mean they're basically eating just like water. That's about it. So, but those are just basically things. So the composition function is if somebody is lactose intolerant, you can't have any part of their diet have lactose in it. If they are also gluten free, no part of their diet can have gluten in it as well because they're going to deal with that. All right, so this one's done for that. Now let's change this color here. I'm going to change this to the blue highlighter. Okay, so this means I'm plugging this right here, that whole thing, where is that now going to go? In for X right here. Okay, it doesn't really show up, sorry. But can you see how that X would be highlighted if it worked? Okay? So that's what we're doing. And this is a big thing you'll use in pre-calculus a lot. It has to do with the derivative function. Okay? So if I take f at x and plug it in, so I have x plus 4. So now I'm going to plug, I had this blank here, plus 4. The blank was an x. Now I'm going to put negative x to the half in there. Okay? So that's what this one is equal to. Okay? So then let's take a look at that domain and see if that's restricted. Well, that's still going to be restricted. It just goes up. So the domain of this one here is going to be still the 0 to infinity. Okay, and I actually didn't get totally done with this bottom problem. Is this domain correct? Help me out. I heard a no, but it was an unsure no. It was more like a question, like, no. No is correct. Why is that not correct? Yeah.
Is it because the limit is already at 0 and -4 is smaller than 0?
That's exactly right. Woo! Nice job. Now, so let me clarify. So this domain here versus this domain here. This is, and let's just deal with whole numbers because I'd be here all day long and I'm all the rest of my life counting up all the decimals in between. This one includes -4, -3, -2, -1, and then it goes from 0. This one starts at 0, goes 1, 2, 3, 4, 5, right? So this one includes more numbers, which we did a compositional function. I can't include more numbers in this. I have to go just as restricted. So this right here is what this domain needs to be. This domain is not correct. I need that to be my domain. That's the most restrictive domain. Yeah.
So does that, with the yellow circle thing, does that determine if the domain is correct or not?
Now, if this had been positive 4 to infinity, then it would have been totally correct, because that would have been a more restrictive. But because it's -4, you're like, oh, I have -4, -3, -2, -1 that I'm also including. No, you can't. You can't just automatically have something that you didn't have. It's like, here's $1,000, which would be kind of cool. Someone just handed you $1,000, right? But what happens if you go and spend $1,600? Just because you had $1,000 doesn't mean you get the $1,600 thing for the price of $1,000. Well, you might be a good negotiator. I don't know, but you'd still owe. So you don't want to owe on these.
$1,000 off.
All right. What else do you want to see? One time for one last one. Two five? You got it. Thanks for asking that one. I hadn't really taught this yet. Let's see, 25 h t at -1. Okay, and then we know that h at x they told us was 3x minus 2. And then they also told us that t at x, and these mean the exact same thing as f at x. That's x to the 5th. Okay? I think you're going to like this problem a lot more. Item number 1. I'm not worried about a domain on this. Dude, I already like it. All right, ready? I'm going to take -1. I'm going to take -1 and I'm going to plug it in right there. Still with me? So if I have t at -1, that means I have -1 to the 5th power. What is negative, 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 negative? Say negative.
Negative.
Good. So -1, or it's -1 to the 5th. Okay. So that's t at 1. So this now means I'm going to take this value, which is t at 1, and I'm going to plug it into here, which means I'm going to then plug it right there. Okay. So -1 to the 5th power is just -1. So I get 3. There was an x right there. In place of that, I'm plugging t at -1 in. T at -1 is equal to, this equals -1. So I'm just plugging a -1 in. There's my answer. So I found out the numeric value of the inside function, found that value, plugged that value in for the variable for the outside function. Okay? You are welcome to turn that in today, but if you need a couple extra days on it, like until Monday, that's fine. Okay? If you wanted a couple extra days, that's totally fine, okay? And there's no penalty on that, okay? If you want to turn it in, that's fine. If you want to turn it in, just bring it up, put it on my round table, and I'll make sure I put it in for you. If you still want extra days, like until Monday, without any penalty, please take that.
I did Is it only
Loud.
Can
you hear? Yeah. Look at my two drawings. They've been alive for the longest time.
I know, dude. It's awesome.
Oh, hold up.
It's
one. This one. It's not recording.
Oh, yeah, dude.
Yeah, it is.
Oh, it's
Yeah,
paused.
it is.
Oh,
it's
it's
recording.
going.
Oh, thank you.
I got you like a
Square root of x would be square bracket 0. In that square root, x is in the
oh boy.
that would make it 0 down.
Okay, so if it's 0,
Yes. We good? Anyone else need extras that I forgot? Did y'all wave to the cameras and do other events in front of it? Too many? Go ahead. You never have to ask. Just go take care of. Oh, God. Man, extras now too. All right. So this is a little thicker. I can go through it pretty quickly because a lot of it is way prior knowledge. When I say way prior knowledge, I totally mean it. All right. So we want to understand the understanding of a one-to-one function, inverse relations, and functions. Then learn how to write them as inverses. Okay. So which represents functions. So hopefully you all remember the vertical line test. If I can draw any vertical line and it only touches my thing once, it becomes a function. This is not because it's a vertical line. This is not because it touches twice. And this one's fine. So these two are the nots because the vertical line test doesn't pass.
It's just not okay.
Okay? So you remember the vertical line test. And the vertical line test just means the domain does not repeat. The domain are the x values. It doesn't repeat. Good so far? All right. All right. Oh, crud. I think I removed your guys' blanks, but I have to take them all out. All right. Oh, wait. Over there. Over there. Go.
Who decided to do the blanks?
I don't know. Someone thought it was a good idea, and it was all cutesy at some point in life, but
I guess they were just like blanking out.
Oh my god.
That was a good one, Sam. I like that.
all right.
Thanks for your appreciation, my dude.
Okay, so one-to-one function. For every value in the domain, there is only one value in the range. Sounds good. And for every value in the range, there's only one value in the domain. The graph passes a vertical line test and a horizontal line test to be one-to-one. Okay, so the vertical line test, that you pass that, and it says, hey, we got a function. And then you do the horizontal line test, and if you do the horizontal line test and it crosses it twice, that means that it's a function, yes, but it's not one-to-one. Okay, this one, does that pass vertical line test?
No.
Sure does. Vertical, horizontal, both look good?
Yeah.
Yep.
So it's a function, it's also one-to-one. Is this a function? Yeah? Is it one-to-one? No. Because the horizontal line test doesn't pass. Okay? This one right here. It's a function. Horizontal line test touches it multiple times. This one is not one-to-one. Okay? What about these down here? Well, that's just a straight line. If I had graphed this, -5,
It's graphed.
is it? Oh.
Yeah, it is.
You guys have a graph?
Yeah.
Best day ever.
Nah, we don't have any graph on ours.
Oh no, that's stupid. No, we don't.
Any graphic sheet.
I don't have a graph.
I didn't have it. All right.
This is the same page, but it's just printed back to back. Oh, never mind. I'm looking at the wrong page. Man.
All right. So, hey, does this pass vertical line test?
Yep.
Yeah. Does it pass horizontal line test?
Yep.
So this is one-to-one. It's a function. This one right here is an absolute value function. It shifts right 3 and up 2.
Doesn't.
It looks like this when I graph an absolute value. Is that a function?
Yeah.
Yeah. Vertical line test pass. Is it one-to-one? No. Touches twice. Okay, so basically a one-to-one function, the domain and range never repeat. Okay? In order to have a function, your domain doesn't repeat. In order to be one-to-one, your range doesn't repeat. Yeah.
So, like, in this case, is it only going to be one-to-one if it's just like an x plus or minus something instead
Could be.
of like.
But it's also this. That's a one-to-one function. This is a one-to-one function.
But absolute
This
value.
is a one-to-one function.
Squared. It's
Okay.
just like never.
I mean, I don't put a whole disclaimer on it. I mean, I think for the most part, parabolas you could probably eliminate. Absolute values eliminate for one-to-one.
Cool.
And then we'll just start there. And then later we might start getting rid of other stuff. Cool? Can I move on?
Yeah.
Yay. All right. So let's graph x minus 3 over 2. All right, so let's go the cheap way. We're going to make a t-table. So I have an x, I have a y value. I don't know, go -2, -1, 0, 1, and 2. Sound good? I don't know, I just had to start someplace. So -2 minus 3 is -5. -5 over 2 is -2.5. Is that okay? And then plug -1 in. -1 minus 3 is -4. -4 over 2 is -2. Plug 0 in. 0 minus 3 is -3. -3 over 2 is -1.5. Plug 1 in. 1 minus 3 is -2. -2 over 2 is -1. Plug 2 in. 2 minus 3 is -1. -1 over 2 is -0.5 or -0.5. Do you feel comfortable with my information?
Yeah.
Okay, we're not in Algebra 1. We don't have to make them whole numbers anymore. We can guesstimate the best we can. So I get -2, -2.5 is like right about there. And then -1, -2 is about there. And then 0, -1.5 is about there. Here, here. Giddy up. Function? Vertical line passes, yes. 1 to 1? Yep. Okay, so what is the equation we graphed? It is a linear equation. What do you notice about the graph of the two lines? Oh, wait, there was 2 lines we had to graph? Where did I miss that? Let's graph that by creating t-table values. Now let's reverse the x and y values. Oh, okay. Now we're going to reverse these. So I'm going to plot the point -2.5, -2. -2, -1, -1.5, 0. Let's see, -1, 1, and then -0.5, 2. If I could connect the dots, you just gotta make the dots bigger. So the blue is the original, the green is the inverse function. The inverse function, you just flip-flop the x and y's. Both the blue and the green are both functions. Both the blue and the green are both 1 to 1 because they pass both the vertical and horizontal line tests. That okay?
Yep.
Ready to move on?
Yeah.
Yay! All right. So inverse is the relation that maps the output values y's to the original relation back to the original input functions. What switch the x and y's is? So if you have 1, 2, then you plot 2, 1. If you have -5, 6, you plot 6, -5. You literally just change the order of it to find the inverse function. The graph of the inverse function is a reflection over the line, the parent function of the linear equations, y equals x. Y equals x is just this line. Okay? So you'll start finding when we have inverse functions of each other, there is a reflection over the basic line y equals x. Move on? I think you had all that. All right. Let's find the inverse. Let's see if you can pick up on this. Agree?
Yeah.
I just changed all the x values, made them y values, made all the y values x values. I kept them paired together with what they had originally started with. But that's all we did. That's the inverse.
Funky.
And honestly, if you can kind of look at this, saying that's pretty simple, inverse functions are pretty simple. And we will definitely explore these a little bit more. Okay. So I want to graph this. I can do this a couple of ways. This looks like it shifts left 2 down 4. Left 2 down 4. That's my vertex. So I have -2, -4 as my vertex. Do I graph at a rate of 1, 3, 5? Because it's a parabola.
Yeah.
Pattern graph works? All right, so if I go right 1, up 1, left 1, up 1, I'm going to get -1, -3, and I'm also going to get -3, -3. Is that okay? And if I wanted to pattern graph one more, I'm going to go right 1, up 3, left 1, up 3. So that's going to give me 0, 0, and that's going to give me -4, 0. So this is what this graph looks like. Does everyone feel comfortable how I got my points by pattern graphing?
Yep.
And I'm not going to have you pattern graph where I'm going to say, hey, you have a vertex of 5.667, 3.712. Go ahead and pattern graph and find the other values. That's just mean. Okay, so by definition, what did I say? How will we find the inverse?
Flip the thing.
Switch the X.
Yeah, I'm going to flip them.
So you only switch the numbers and not like the signs.
Right, the signs do not switch. That's the inverse, agree? Now, just know if I have -3, -3, the -3's flipped each other, but they look the same. All right, so let's graph. -4, -2. Agree? -3, -1. -3, -3. 0, 0 stays the same. 0, -4. So I'm going to tell you from the green to the red is the inverse. Is that okay to say that? From the green to the red,
No.
Yes.
the red is the inverse of what the green graph is. Now, I will tell you, the red is not an inverse function.
No. It's
Why is
just
that?
Because it doesn't have
Vertical line test doesn't apply. So what we'll start having to get to is we have to start restricting. Yes, she's
to where it's a function.
yeah. So this.
So it'll only be like the upper.
Yep.
Yeah. Okay.
So we're gonna have to start saying, hey, that's the inverse function, but you had to restrict it to get that.
So like
But
the
do we have
thing
to
we
do that?
graphed.
I don't know. Like,
I'm just kind of
That's
giving you
just in
that
the
glance.
future.
I don't know what the future slides have because this is the first time I've seen this lesson in
okay.
25 years.
Yeah.
So
So it's like kind of like the thing we graphed like 4 days ago or something.
sure.
Nice.
May I move on? Okay, so all I did is I graphed the parabola, found some extra points by pattern graphing, flip-flop my x and y values to graph the inverse, and then I kind of have to restrict the inverse to so it's a function. So the lime green or the neon green had to be there to show that's the inverse function. The red's the inverse. The neon green is the inverse function of that. So we had to restrict it. Move on. Whoop. Okay. To find the inverse of a relation that is given x and y, you switch the rules of x and y, solve for y if possible. Okay. You want to see how easy this is?
Yeah.
Okay, so here's my original. So in the period, that's not a decimal, that's just a period. I'm going to do this, and I'm going to stop here for a moment. What did I just do? I switched the x and y. What do I do when I find the inverse using points? I flip-flop the x, y. And then what you do is you solve this for y. So then I get x plus 4 equals 2. And so then I get y equals x plus 4 divided by 2. This is the inverse of that. That's it. You literally take your x and y, you flip-flop them, and then you solve for y. Now, if this was f at x equals 2x minus 4, you change f at x to y equals, because f at x is just functional notation. Change it to y equals, and then flip-flop your x and y's.
Can you
So
simplify that one? Because
I just leave it. Just leave it. Just leave it. Trust me. It'll serve you better later to leave it than worrying about the. That's like taking a fraction and deciding is it a mixed number or an improper fraction. Now you're learning improper fractions are the way to go. Mixed numbers are just the dum-dum's way of talking about how much pizza you had left. All right. How do I do the inverse of this one? Switching the x and y. So do you agree with this? And then I'll do this in a different color. So I'm going to multiply both sides by the reciprocal. Make sure you distribute that. So then it's going to give me y equals negative 3 over 2x plus 18 over 2, which is 9. And that one simplified nicely. That's the inverse function of it. What does an inverse function really do? Y'all got one of these? I know yours is cooler than mine, right? So mine reads my index finger. Or I can plug in a 6-digit code. What am I doing when I do plug the code or do my index finger? I'm doing the inverse function of the lock to unlock the phone. Okay, so there's a mathematical function that I have in place. When you get your iPhone or whatever phone you have, and it takes your fingerprint, that fingerprint's overriding the access code that you had in there, which is an inverse function. And what it literally does is it takes your function and it plugs it into the other function. And if the other function solves to be x, that means they're inverses of each other. And that would make more sense in a little bit. But that's a place that this is definitely used. Which of the graph shows functions? You know this. Let's move on to this. Okay, so an inverse relation and its inverse relations whenever both relations are functions. Did I have things to remove on this one? Okay. This is what I had just said for you about your phones. If you have two functions given to you, you plug one of the functions into the other and you solve it. You break it all the way down. If it breaks all the way down to become x, that means the two are functions of each other. Okay? We also denote inverse function as f to the negative 1. Okay, that means the function to the negative 1 is, we're looking for the inverse. Okay, so let's apply this to these next couple. Okay, we got that already. All right, I want to know these are inverses of each other. So there's one of two things I can do. Now I'm going to tell you the way that I want you to do it, and then the way that a lot of people are going to resort to, and it's going to goof you up later in your calculus and pre-calculus class. The way I'd like you to do it is pick a function. I don't care which function you pick. Rachel, you pick one. F or G? Choice. G? She picked this one. What I'm going to do with that one is I'm going to plug that in right there. Cool? So if I plug it in right there, I'm doing a composition of a function. I'm plugging one function into another. So I have 2 parentheses minus 4. So I have 1/2 x plus 2. Is that okay so far? Where those parentheses are, where the x had been.
Oh, and you want 0?
So then I want to distribute here and here. So what is 2 times half? X. What's 2 times 2?
4.
Minus 4. If my result, if I take one function and plug it into the other, and I simplify it, and it simplifies down to x, that means they are inverse functions of each other. That's what my fingerprint or my 6-digit code does. There's a math function here that's waiting. It's preset. It's already put in my phone, and there's another math function over here. It's going to say, okay, as soon as that passcode's put in, I'm going to take this, and I'm going to move it right here, and it's going to go in place, and it's going to generate x, and it takes me to my home screen. That's the thought process that's taking place on your phone. That's actually the program that's taking place on your phone. Okay? Some people are like, yeah, but my phone just knows me. Okay. It's getting to know you because it's learning from it because of functions plugging into functions. Someone asked the other day, how do those Google translators work? Did they plug in every word in the English English language and took every word in Spanish and French and they linked them all to each other? No, they created an algorithm, because some of you know when you take other languages, our subject-verb agreement is different in English than it is in French. And it goes with a mathematical algorithm that goes with it. And then it figures out the probability of what is the next context of this. So the more and more you use a translator, the more and more it starts learning from itself, because you have to go in and you make a correction. As soon as you make a correction, it sends that iteration back to the subroutine, makes the correction, so it will be corrected each time you use it. So the more and more you use a translator, the better and better it will become. Okay, are Google translators 100% accurate? No. Can you get by if you go into another country, you had your phone, you talk into it? If you're in, China, you're like, I don't speak Chinese, but you go to the Google translator and you speak in English what you want, and then you play it for the person on the other end, they hear it. Are they going to figure out? Yeah. If you're like, dude, I need to go to the bathroom, it might not recognize dude, but it's going to recognize the bathroom. And that person at the other end is going to hear probably some of the context of the bathroom, figure out, I can really have fun with you saying, yeah, I'm going to send you down to the dock where there's not one, or I'm going to point right over there where there is a restroom.
Nah, man, water is the bathroom.
Okay. I love this kid.
Dude, I love the notes. The notes.
All right, let's check to see what these are. I'm going to pick this one, and I'm going to plug it in there. Is that okay? So again, it doesn't matter which one I plug into which. I want to just verify these are inverses. So I have 8x to the third in parentheses. It's going to be raised to the 1/3 power, all divided by 2. Okay? So notice I'm taking 8x to the third and plugging it in just for x. The x still has a third that it's raised to, still divided by 2. All right, this is where you might get goofy. This is the same thing as third root. So what's the third root of 8? 2. What's the third root of x to the third? Over. Cancel, cancel. Are they inverses?
Yes. How did you get 4 of them?
I crossed off the 2. Sorry about that.
That's the last
Pretty
one.
cool. That was the last slide?
Yep.
Are you kidding me?
You're
I made
killing
it
it
through.
today, Mr. Stern.
I made it through like 19 pages with 4 minutes left.
Killer.
Sweet. All right. So let's do this. Worksheet J.
Every other number?
Odds.
Odds. I'm with you.
No, even.
Odds.
Even.
I heard odds first.
No, even to
Even.
All right, and then if you needed more time on last night, you have up until Monday to get it in still for full points.
Did we turn in
Check your. Can you check your grades real quick?
Oh
See-
wait, yeah, no, it's right here.
Okay.
Yeah, are we turning in odd?
All right. Hey Grant, you have a quiz you got to finish. Cooper, you have to. Landon, we have a plan, right?
Yeah.
Sometime by the end of next week. Cool.
How much did you see how much I level?
I once had one at 11:30. It started at 11:30. And I'm like, how do they get away with that? Like, how are they allowed to
Maybe 2 or 3.
They kind of got me at These are like really bad stuff. You get actual stuff. Like, not